If we look at this example, we have a 40 kilogram mass ball that is located on top of a 50-meter high ramp. There's two things we want to find out. At point A, what would the object's velocity be? And after traveling over this 15-meter section, a 15-meter long section of friction, what would the velocity be at B? Hopefully, you're getting to the point where you realize that at A and at B, the energy will just be kinetic. However, at B, it has to be less because this friction is going to take some of that energy away. It's going to convert some of it to heat or sound. So hopefully you realize that the velocity at A and the velocity at B cannot be the same because B has less energy as a result of this friction. All right, so how do we go about finding this velocity at A? Well, again, we always have to choose our two starting points or our two locations. A good one is generally the start because I do have enough information here to find how much energy I'm working with. And then A, obviously, because that's where I'd find the velocity at A, would be at point A. So if I analyze between my start point and point A, there's no friction. I'm not told that there's any outside forces. This is naturally, due to gravity, going to roll down the hill and approach point A. Therefore, there is no work occurring between my start point and point A. That makes this problem very easy. I list out my energies. I don't have to worry about work. So it's my gravitational potential, my kinetic, and my elastic potential on one side must equal those three added up on the other. At the top of this hill, if we assume the ball is not moving, I only have gravitational potential energy. So I get rid of the other two. And if I look at point A, it's on the ground. It has no height. There's no spring. Therefore, it only has kinetic. Hopefully, this makes complete sense. The potential energy, the gravitational potential energy at the top became the kinetic energy at the bottom. We're at point A. When I plug in my equations, mgh equals 1 half mv squared, this being the height at the top of the hill, this being the velocity at the bottom, I plug in everything I know. Once I do that, I have just one unknown, and if I've solved this all correctly, I should be able to determine that at point A, this ball is traveling at 31.32 meters per second, because it has to have the same amount of energy at location A. However, it's all stored in the kinetic energy and the velocity of the object, as opposed to the height and the gravitational potential energy of that object. So a very straightforward question. Anytime you don't have work being performed, you don't have to account for it, and your equations are these simple: GPE plus KE plus EPE on both sides. Cross out whatever you know doesn't exist at those locations. We get a little bit trickier when we try and find the velocity at point B, because at point B, we have to realize, yes, the energy I started here is the same amount of energy I had at point A. However, as I slide across this frictional surface, I generate some heat, some sound, and that dissipates. That literally leaves as heat or sound, and I no longer have it at B. It's still in the universe. It's still a part of the total energy in the universe. It's just not a part of the mechanical energy that the ball possesses. So I still have to choose two locations. It hopefully makes sense to choose my starting location, which I have already determined the energy for, and point B, which occurs after all of this friction. Now, because there's this frictional section in between my starting point and point B, I have to realize that work absolutely does occur between these 2 points. So all I'm going to do is list out the same equation, GPE, on both sides. However, I have to add work to the starting side to show that the starting energy plus whatever work occurred over that frictional section, that has to be equal to whatever is left over at B. When I cross out anything I don't have, because this only has GPE and this only has KE, I realize that the GPE plus the work performed on its way to getting to point B must equal whatever kinetic energy is left at point B. So if I plug in my actual calculations or my equations, mgh, which is the GPE at the top of that first hill, the work performed is F delta x, cosine of the angle between these two. And on the other side, it just has to equal 1 half the mass times the velocity at point B squared. We hopefully realize that it should be less than 31.32, because if the friction wasn't there, it would just travel at a constant 31.32, but this friction is going to lessen that a little bit. So plug in everything we know. The mass is 10, gravity on Earth is 9.81, and the height of this initial hill is 50 meters. The force in the work is the 10 newtons, we're told that up here. The displacement is 15 meters. And because the ball is moving to the right, but friction opposes the motion to the left, that means the angle between them is 180 degrees. So that takes care of the left side. On the right side, 1 half mv squared. Well, I know the mass is 10. I don't know what the velocity is. But now you hopefully see that I have one equation with one unknown. And if I plug that into my calculator and solve correctly, I find that that ball is traveling at 30.84 meters per second, which makes sense because that ball has absolutely slowed down. I wouldn't say by a tremendous amount, but friction is only 10 newtons over the course of 15 meters. That's not a very large amount. But in order to account for work, I just have to add plus work to my starting side and then solve the rest of the problem the same exact way, making sure I incorporate this work equation.